Oh.
Okay. Thank you. Okay, so before we start, we need to understand how runtime detection tools even work, right? Because in order to understand how to bypass them, we need to understand how it works on the surface. So we divided it into three main parts. We think it's the easiest to understand it that way. So the first part is the telemetry collection of those runtime detection tools. The second part is the rule processing. What do they do with the telemetry collected? And the third part is to notify to the user once a detection is found. So, wait. So many technical problems. Sorry, okay. So the first part is the telemetry collection, and we are going to focus today on runtime detection tools that are running on the host, mainly, not like API security and those sorts of things. So the main telemetry being collected from the operating systems are things like processes, files, network activity, system calls, permissions, and especially when today we are going to focus more on the cloud era of runtime detection. So the events are also being enriched with the context where they are running at. So if in the 2000 the antiviruses would just send the telemetry on the processes, this time when we are running in containerized environments such as Kubernetes, or if we are running on EC2s in AWS, so the security vendors also enrich the events with some extra data, for example, the pod or the namespace in the Kubernetes and the container name. So now that we understand which telemetry is being collected, we need to understand what the security vendors are actually doing with this information. Now, they can do various things, but the new tools, like more of the cutting edge tools, are trying to do more of anomaly detection, right? Because the traditional detection of hash scanning or byte pattern scanning and all the YARA rules that are being used for many years, they are good, but we see that it's not enough. Like, attackers are still breaching in, they are still finding ways to bypass. Today there was a talk here about bypassing all of those. So the newest player is trying to create something called anomaly detection. For example, assume you are running in a Kubernetes cluster and we have a runtime detection tool that wants to monitor for attackers on this cluster. So what some vendors are doing are actually building profiles for the applications running in Kubernetes. If you think about it, your operating system, like Windows at your home PC, it's a bit unexpected. Like every day you can do something new in the computer. But when we are talking about containers, the behavior of a container is pretty expected. Like it's an image, it's pre-built, it's running something. If you record it for enough time, you can understand what the container is doing. So for example, we can build a profile for an application, we can record the processes, files, system calls, and network activity, and therefore enforce anomaly detection on top of that. We can also write some custom rules, as we are going to see. And the last part, after we understand what the tools collect and what do they process, is the notification to the user. And this is the easiest part, obviously. We can see the alerts in the UI, we can get notification in Slack, Teams, PagerDuty, whatever platform you're using. And of course, some of the tools are also trying to respond to the attack or prevent it. So now that we understand how runtime detection tools work, we need to understand how the telemetry is actually being collected and how we can tamper that. Now, the most widely used technology today by security vendors is eBPF. And I'm going to pass it to Nir to explain about eBPF, and then we can see how we can bypass that.
So now, after Amit explained about how do runtime detection tools actually work, before we will dive into eBPF, let's talk a little bit about the kernel. So when you're writing a process, maybe a Python process, that need to open a file, write to a file, then close a file, it actually runs in the user space. And when you're writing it to a file, you actually want to interact with the storage or with the hardware, or if you are sending packets, you want to interact with the network interface card. And how do you do it is actually using the kernel. The kernel is a very complicated piece of code, which is actually the heart of the operation system. It has management memory, it has different drivers and kernel modules, which are basically allowed you to interact with the hardware using the kernel modules. So if your Python process wants to open a file, you actually want the kernel to load it to the memory and bring you back an identifier, which is called a file descriptor. And the way you are interacting with the kernel is using an API called system calls. So if I would like the kernel to open a file for me and map it to the memory, I'm using open system call and then write this call in order to get a file descriptor and be able to write to this file. So the next question you would like to ask is, why do I want to run in the kernel? So every time I'm doing a syscall, there is something called a context switch. Context switches happen every time I want to move between the user space and the kernel space, and every time I'm coming back with an answer from the kernel into the user space. And this context switching is taking time. So if I'm running only in the kernel, I'm not wasting time on context switching, and I can run much faster. The second thing is that if you're running in the kernel, you're actually a little bit like a God mode. You can do almost whatever you want. You can read from wherever you want, every struct you want. You can write to almost every piece of memory you want. And it's pretty cool, and you will see it in the next slides. So we understand what is the kernel. We understand why we want to run in the kernel. But how can we write code that it will run in the kernel? The first option is changing the kernel source code. I can open a pull request, for example, to the Linux community, send them some mail, and then after a couple of months, if they would like us to merge this commit, they will merge it, and then I will need to wait a couple of years until my clients see this code in the kernel. Ain't nobody got time for that. The second option is writing a kernel module. So you're writing a kernel module and then ship it to your client. But there are a couple of problems with this method. The first problem is that it probably will be break every time a new kernel version will be released. And the second problem with developing kernel module is that it might crash your kernel. Who in this audience heard about the CrowdStrike incident? Lots of people. What's happened there is that Falcon, the runtime detection tool of CrowdStrike, it's actually a kernel module, and there was a panic exception in the kernel module, and for this reason, the whole operating system crashed. Why it's crashed? Because when you are writing a piece of code in the kernel and you have an exception, there is no other code that will catch it. So for this reason, the whole system is panic. So what is the solution for this? eBPF. eBPF allows you to extend the capabilities of the kernel in a safe way and a more efficient way. You can run sandbox program in the operating system. And Brandon Gregg, who is one of the eBPF guru, said that eBPF does to Linux what JavaScript does to HTML. So if you want to add a feature to observe your app, or maybe make your app more secure, you can just ask one of your friends who know how to write eBPF, or today ask one of your favorites LLM to write an eBPF code for you, and then just inject it into the kernel, and you will have lots of fun. So how does it look like? We have the user space, we have the storage hardware, and we have the Linux kernel. eBPF allowed me to hook in different places. I can put a hook in a syscall, whether it's open syscall or write syscall. I can put it in the IP stack and interrupt in different places. I can use technology that called XDP, Express Data Path, and manipulate and read packets in a very fast way on the network interface card. And whenever a function, let's take for example an open syscall is triggered, the code that is actually running is also my code, whether it's in the start of the syscall or when it's in the end of the system call. Let's take a quick look. You can see only in 7 lines of C code, I am be able to hook the return from execv. Execv is a common syscall that happens every time you are generating a new process. So what will happen here is that I will be able to extract the process name of the process that just ran and send it using perf submit back to the user space. Let's see a quick demonstration. On the above pane, you can see IPython. On the bottom pane, you can see OpenSnoop, which is one of the most famous eBPF example program. OpenSnoop actually hook the open syscall and open at syscall, and every time I will open a file, what will happen is it will retrace it. You can see it trace the process name, I'm getting the path, and also the file descriptor. And if I will open another file, for example mag, I will be able to see it down. That's all. So as I just said, the CrowdStrike Falcon BSOD issue, you say, okay, so we have eBPF. Why does it safer than kernel modules, right? It can also crash your computer, no? So not exactly. eBPF use component that's called verifier. Verifier is a piece of code in the kernel, actually a very complex and long piece of code. You can see it in the kernel source code. And what this is doing is actually verify the bytecode of the eBPF before it loads it into the kernel. It checks a lot of stuff. It checks that all the lines of code in your code is actually reachable, that you don't have infinity loops, that you do not have null dereference, and etc., etc. And this allows you to load an eBPF code in a safe way without the risk of crashing the kernel. So if a couple of years ago you want your clients to install a kernel module, and I guess they will say, no, it's risky, and they are actually right, today you can ship eBPF code. And as you saw, lots of companies today and vendors today build the runtime detection tool on eBPF because it's much, much safer. So we talked about how do runtime detection tools work. And now for the most interesting part of this presentation, let's see how can we bypass the runtime detection tools. And for this, Amit.
Thank you, Nir. So now that we understand how everything works, we understand how runtime detection tools monitor us, we understand the underlying technology, let's see how we can trick it. So let the games begin. The first technique that we are going to talk about is tampering with eBPF maps. Now this technique is already known for a while, and let's talk for a second about what are maps in the context of eBPF. So we said that eBPF is so awesome, it's not crashing, we have the verifier, we have the different components, different hook points, and maps is a crucial component in eBPF because when you write eBPF code, by default, all the code is saved on the stack. But as you know from your favorite programming languages, sometimes we want to save some memory on the heap, right? If we mess with a lot of data, we cannot put it all on the stack. So in eBPF, the way to do it is put the data in the maps. Now, a map is like any key value storage, like you know it from a dictionary in Python, for example, the same concept. And it's mainly being used for two things. So the first one, storing a lot of data, which we want on the heap. And the second thing is to send the events that we trace. For example, the execv that we trace in eBPF, we want to send it to the user mode, to the actual agent controller. Now, this is being done in different ways, but most of them are being like relying on maps. So it means that if we can tamper with those maps, we can actually do some interesting things. So in this technique, actually, we're going to show how when we're tampering with the maps, we are completely disabling most of the famous runtime detection tools. And before kernel version 5.8, all you need was capsysadmin, which is basically root. But after kernel 5.8, Linux are always adding more capabilities, and we have capsysBPF. So it's enough that you have capsysBPF, and you can actually tamper with the eBPF tools. Now, the interaction with the maps are very simple. For example, here is a simple program that lists all of the eBPF maps on your system. Now, the important thing to understand is that maps are global kernel objects, which means anyone with sufficient permissions can access them. And in this case, we listed all the maps in the system. So let's watch a demo. Okay, so on the top pane, we actually have Tetragon, which is a runtime detection tool developed by Cilium. It's a graduated CNCF project, and it's being used in many environments. Now, we run it in the top pane, and in the bottom pane, we get etc shadow, okay? Sensitive file, we want to get an alert from our runtime detection tool whenever we touch this file. So let's see it, we get, and as expected, we get the alerts, okay? What do we see? We see the process execution of the cat. We see the read system calls because we touched a sensitive file, otherwise we wouldn't see that. And we see the exit system call. Cool. Now, what we're going to do is we wrote a special program that actually deletes all the keys from the map of Tetragon and then cat etc shadow again. So let's see what happens. Okay, we get etc shadow, but this time we only got an alert that the process was executed. We didn't get an alert when someone accessed the etc shadow. And this is because we actually kind of disabled Tetragon by telling it to not monitor us. And this is a very important part because you need to understand that those runtime detection tools run in many different environments. For example, a lot of them are running today in cloud environments like Kubernetes. And if I'm monitoring Kubernetes, I don't want to monitor all the processes that are on the nodes. I want to monitor only on the containers that are related to the Kubernetes. Now, a container is just a process. So I will hold the map with all the processes that I want to monitor on. And if, for example, an attacker tamper with the maps, delete the PIDs from the maps, basically it's staying unmonitored. And the cool part is that the runtime detection tool doesn't really have a way to know that it happened because it just relies on the maps. Now, we took it even further. And I guess you all used ChatGPT, right? Or any other LLM. So we thought, why not making LLM attack eBPF? So what we did was, this time we took Falco, another very known runtime detection tool, also a CNCF graduated tool. And it's actually being used in many companies. So on the bottom pane, we have Falco. We're going to do the same thing. On the top pane, we are getting Etsy Shadow. Okay, we got an alert from Falco, as expected. A sensitive file was accessed. And this time what we did was we actually created a Python program. Now, if some of you heard of the new MCP protocol by Anthropic that allows us to connect tools to LLMs. So we actually wrote an MCP server that provides eBPF tools. Basically what it means, now imagine ChatGPT have access to the BPF system call to do activities with eBPF on your system. So, for example, you can see here at the top, it's a bit small, maybe you don't see it, but we gave it tools like get map details, delete all keys for map, enumerate the eBPF programs installed on the computer. So, we gave it a query, and we said, hey, I'm running the Falco eBPF tool to monitor my system. I want you to find all the eBPF maps in the system, find the maps that are related to Falco, and delete all the keys from those eBPF maps. Now we let it run. We can see it's doing some tool calls, actually calling the BPF system call, enumerating the machine. And in the result, he said, hey, I found several eBPF maps, blah, blah, blah of AI, and he gives us the name of the maps. I can confirm it's actually the maps of Falco. Awesome. Now, we're going to do the same thing. We're going to get etc shadow. Okay. But this time, we see Falco is sleeping. Nothing happened. So the same trick that worked on Tetragon worked on Falco, this time with AI, actually pretty cool. Like gives us a hint into the future of offensive security maybe. And you can even take it further. You can connect tools, for example, to GitHub or Google, and then the LLM can even search in the Falco repository, which is open source, even find some more interesting things. But this just demonstrates that there is a bit of a problem here with eBPF. It's actually not that trivial for defenders, for the security vendors that write those tools, to protect from this kind of attack, and we're going to talk about it. Okay, another cool technique that most of the runtime tools that are based on eBPF are vulnerable to is time of check, time of use. Now, this backlash is very interesting because it's pretty hard to defend from if you don't have the right hooks in place. And it basically happens when you're copying buffers around. It's very common in this type of scenario. So we said with eBPF, we can hook almost any system call, right? And this is what the vendors are doing. So let's imagine we are putting a kprobe, which is a type of a hook, on the system call. Let's say an open or exec. Now, the data that's being transferred to this system call, for example, we want to open a file. So we pass the path to the file, right? And in the time of check, in the time of the hook, the eBPF is being executed, let's say the path is actually something legitimate. But in the time of use, we will make it be etc shadow, our sensitive file. And how we can achieve that? Basically, we're going to do a very simple thing. We're going to write a C program with a buffer, and we're going to create two threads. One thread is going to write etc shadow into that buffer, and the second thread is going to write any legitimate path on the system. Now, they are both going to run, and of course, it's not 100% accurate that it will work, but sometimes, and actually in pretty high probability, it does work. So let's see a demo of that as well. This time, again, we are abusing Tetragon. Sorry, Tetragon. In the top pane, we have Tetragon. On the bottom pane, we are going to create a symlink to etc passwd. Another alert that the runtime detection tools are doing. So this time, it alerted on us for creating a symlink over a sensitive file. So what we're going to do is we're going to run the program I just told you about, the time of check, time of use attack. This time, we only see process execution and exits, but we don't see a symlink over a sensitive file. Because at the time of the check, the path was legitimate, but after it, it was a sensitive one.
So let's see another technique, this time using symlinks. So in this demonstration, we will use Falco again, one of the most famous runtime detection tools today. And as always, we will cut /etc/shadow and get an alert as expected. Why we get an alert? Because Falco identify the hook syscall, and you see we are opening a sensitive file. Now this time we're gonna use symlink. We will create a symlink to etc/shadow to just a file in the temp directory. And as expected, you can see that Falco just identified about creating the symlink. How we did it? It actually hook the create symlink syscall and check and see that is the opening a sensitive file. I create a symlink to a sensitive file, and we get an alert. But this time, we will cut the file that we created the symlink to, the /temp/ist. We got the data of /etc/shadow, but this time, Falco didn't identify us. So you might say, okay, you can read the /etc/shadow many times you want and will not get caught. But the first time, he alerted. He sent an alerted on you, and you are right. And the trick is kind of even, because on one side, he sent an alert on us, but on the other side, we can read it how many times we want. And this demonstrates a core problem with eBPF. We said that eBPF is great, and is safe and efficient, but it's actually very limited. And because of the limitation of the eBPF, it's very hard to write complex logic. And resolving the symlink back to the original directory is considered to be a complex logic. And that's why a lot of vendors that develop runtime detection tools are vulnerable to this kind of methods. Another option is to use alternative syscall. By default, a lot of runtime detection tool hooking a sysenter and a sysenter open. And this kind of hooks allows them to know when someone opens a file. But in this demonstration, we will use open by handle@, which by default also today are not get hooked. And for this reason, you can see that in the above, I'm cutting /etc/shadow, get an alert as unexpected because we open a sensitive file. But this time we will use another program, and the program we will be used is using another syscall. You can see that we cut the /etc/shadow using this program and not get an alert. So it's pretty cool, and lots of different vendors also vulnerable for this. And yes. Another option is to don't use syscalls at all. And I don't mean do not use all the system calls, but you can implement the syscall that you don't want to be alerted using other tool. For example, you can just allocate the memory, load the dynamic linker, map the executable into the memory, and jump to the entry point. And by this, you will not execute the execv system call. By the way, there are lots of implementation for this on GitHub, and you will not be caught by a runtime detection tool. Another option is killing the agent. Every eBPF program needs to have a user mode program that will manage this eBPF. So, as Amit said, if you are a runtime detection tool, you have a list of all the process ID you want to monitor. You save it in the user space and write it to the map into the kernel. So if I just kill the user mode process, the runtime detection tool will be actually asleep. Of course, that in order to kill the agent, you need to have enough permissions, and you need to have the access to the same PID namespace. But after you do it, you can do whatever you want on the machine without getting caught. There are ways to mitigate it. For example, you can use BPF override return to stop the killing of your specific process, but also it's enter only on a newer kernel versions. And you can use KRSI, which is a kernel runtime security instrumentation. We will talk in a couple of slides.
Okay, so another very cool technique, we already showed some techniques that are kind of like weird situations where the eBPF hooks don't have the right tools to handle those quite of simple attacks. And another one of those attacks is event exhaustion. So we talked a lot about maps. Now the thing about maps is that when you create a map, you actually set the size, how many keys can be in that map, how many elements. So usually vendors don't want to put too much because then it allocates a lot of memory and their agent is consuming a lot of memory. And when running in cloud environments where you don't have a lot of resources, so the maps being allocated are pretty small, which means an attacker can exploit it again in order to, for example, read the sensitive file. So what an attacker would do, he would flood the system with legitimate events. Imagine just creating a program in a loop, sending a lot of events, like the open events to /temp/something, and then I want to read it etc shadow. So after I bomb the machine with like 20,000 events, I'm going to send my one sensitive event. The map is flooded with events. Therefore, there is something in eBPF called events drop, and this will happen. And then you will actually bypass the agent that way. And of course, we gave a lot of example of opening a sensitive file because it's very trivial. But imagine taking that, actually writing your own tool or rootkit with a lot of different types of system calls. And you can actually bypass all of the modern runtime detection tools. And there is another very cool technique that we want to show you today, but unfortunately, the responsible disclosure timeline is still not over. So we found a very cool way to bypass most of the runtime detection tools today, a very generic way to make a lot of system calls without being detected at all. And so follow us if you want to hear more about it in the following months. So we showed you a lot of techniques, and as you might see, it's not very complicated. Like we didn't create here any unauthenticated chain of 0 days and RCEs and everything, but the main idea that we wanted to say here is that there is a core problem, and something like someone needs to do something about it. There is a gap between what the security vendors are thinking their security tools are doing and what they are actually doing. So this brings us to the last part of the talk. We understood how runtime detection tools work. We understood the technology. We saw some very nice bypasses. Now let's talk about this gap. So in order to understand the gap, we need to take a look into the past and to the future of security hooks, how it all started. Now we actually wanted to start with Windows because we feel like Windows has some more miles when we're talking about creating an antivirus or something to detect malware. Now, back then, if some of you remember, the way the antivirus software like Avast or Kaspersky or any other antivirus software would monitor your Windows machine is to hook a table called SSDT. Basically, it's the system call table in your kernel. This is how the operating systems know which function to execute when, for example, you want to open a file. Your operating system is doing the system call that we talked about, and the system call in the kernel is being resolved in this table. So what all the antivirus software would do, they would all hook all the functions in this table. It was a complete mess. No one, like, they were hooking each other and they were creating a lot of the CrowdStrike BSODs. It happened a lot in this time. So Microsoft decided, let's put an end to that. We don't want everyone doing whatever they want in the kernel. We don't want things to be unorganized. And in the newest Windows, you cannot really hook this table anymore. It's still there, but you cannot hook it because it's protected with mechanisms like PatchGuard or HVCI. Now, of course, we're not going to get into those in these talks because it's a 2 days lecture just about them. But we need to understand there was a problem here. So what Microsoft did, they created a new way for security vendors to monitor. They created a mechanism in the kernel called notification routines. This is basically what all of the security vendors today in Windows are writing callbacks to this mechanism. It allows them to see processes, threads, images, objects, registry, and see the activities before they happen and after they happened, and they can inject DLLs, they can inject all sorts of things in those routines. In addition, they gave us a platform called mini filter drivers. It's basically allows us to view I/O operations and file system operations. It's also running in the kernel space. And for networking, we have WFP and NDIS, which is a bit older. But we can see something interesting because Microsoft understood that they need to create an organized platform for security hooks. At the end of the day, security is very important, both for Microsoft that today is shipping Defender and both for the antivirus software. So they create a pretty good structure, and of course there are more mechanisms. But the problem, it's still not enough. We can see that the vendors are actually really likes to hook system calls. And for example, you can see Avast, which is a famous AV software, have the method of infinity hook, which is very interesting. You can go read about it, but basically allows them to hook all system calls. There are other techniques like Shadow Walker, which is giving you the option to manipulate memory pages. And there are a lot of user mode hooks techniques. We put here too, the IAT or hot patching. But the main idea to understand here is that there is still a gap. There is still a gap between what the operating system provider gives to the security vendors and what the security vendors actually want. And this gap creates issues, create those tiny bypasses that we showed you that at the end of the day can be built to something much bigger. Now, let's talk about Linux, because we talked a lot about Linux. So the old way of Linux was kernel modules, as we said. It was netfilter and IP tables for networking. It was seccomp to view system calls. We have ptrace, right? The famous ptrace to do some injections. But we talked a lot about eBPF, right? So actually, even with eBPF, there are the new eBPF, what is called KRSI. Now, we mentioned this mechanism when we talked about killing the agent. Now, in Windows, for example, the antiviruses contains modules of anti-tampering, right? The antivirus software doesn't like that. Even if an attacker has an admin permission, they don't want it to disable the antivirus software. Now, in Linux, it doesn't really exist. Like the security vendors, as we showed you today, all the open source tools, none of them implement anti-tampering mechanisms. And the reason is that they don't have a lot of tools to do it, especially with eBPF. So if we look on the left side diagram, we can see the flow of checks that the system call is going through. So for example, the system call open. First of all, we do the inode search, right? We want to see if the files even exist on the machine. Then we have some more checks until we get to the security module layer. Okay? Now, security modules, you may know them as SE Linux and AppArmor, but Linux added a very cool way called KRSI, which is basically you can place eBPF hooks just as you would place them on system calls, but you can place them in this layer. And it means that you get two benefits here. The first one is that it's almost guaranteed that your hook is going to be called, and it's very important because as we saw with the hooks on system calls, we have a lot of problems like time of check, time of use, and the bypass of not using system calls. But in this case, the LSM hook is almost guaranteed, and today there is not really a known way to bypass that. But the other very important thing that LSM gives us is the ability to actually change or respond to the system calls. So if you remember at the start, we showed you how to write a hook on the execv, on the return. Now, with the other hooks like kprobes or tracepoint or raw tracepoint and uprobes, you can't really do anything. You can only read. You can only monitor on the system call, but you cannot really change the values. You cannot really prevent from the system call to happen. Now, with LSM, you can. And this is very powerful. So, for example, if a vendor wants to detect its tool from someone just killing the process, you can put a hook on the system call with LSM, and you can actually see that if the kill, for example, is not coming from your agent and it's coming from an external process, you can just block it. And up until a few years ago, it wasn't really a thing. Now, LSM is always evolving. It's quite a new mechanism. It gives us visibility, like as of Linux 6.14, you have 270 places you can put LSM hooks. And it gives us visibility into file system, processes, sockets, and more. So I think like the most important thing is that vendors need to understand that placing hooks is not a universal solution, right? We need to actually see what are the vulnerabilities in those hooks. And with LSM, it's pretty interesting. Now the problem is not a universal solution because, first of all, it's only enabled on the newest Linux versions. And moreover, for some reason, a lot of the Linux distributions are having a hard time to adopt this mechanism. Like only in the recent Ubuntu releases, for example, they enabled this mechanism by default. Otherwise, you need to actually turn on a flag in the bootloader and restart the machine, which of course it's not going to happen, not in production in any way. So there is still a major gap here that security vendors are overlooking. They just accept the situation as is, and therefore, like we also, the responsible disclosure that we wanted to tell you about is actually, if LSM was in place, nothing would happen. So I think we can finish with a quote again from Brendan Gregg. Thank you for the wonderful quotes. It says, taking eBPF observability tools as is and using them for security monitoring would be like driving your car into the ocean and expecting it to float. And this is exactly the situation we see in the market today. All of the vendors that are providing security for Linux, they all adopted eBPF, which is great, but they are just overlooking the security gap here. And they just use the observability capabilities of eBPF, and eBPF was built for observability and tracing. It wasn't built for security originally, and they just, we can say, abuse it. So we have the kprobes, the trace point, the raw trace points. The vendors are hooking any system call. They are happy, but also the attackers. Thank you for listening, and if you have any questions, you can feel free to ask. Yes. Sorry, can you speak louder?
I wanted to ask if maybe you tried maybe the time to check to time to use method against the runtime detection tools that are based on kernel auditing framework, if they are applicable, or any other of the techniques that you mentioned that are applicable.
So we actually didn't try it on any vendor using kernel modules. We more focused on the eBPF ones, but even if you're using a kernel module and you're not taking, like, you're not aware of this kind of attacks, you're still vulnerable, because even with kernel modules, you choose what you're hooking. So if you're hooking the wrong place, or you're hooking too early on the stack, then you're going to be vulnerable as well.
Okay, thank you very much.
Thank you.